Hello, my name is Burak and Saleh was my partner in this project. We focused on near memory processing approaches in this project. As you might know, there are two significant issues where the first one is memory technology develops slower than the processor technology, even though processing units have had a high performance already. And second one, architecture grows in scale and memory capacity. These two significant issues creates a performance gap between processor and memory technology, which is highlighted as both on-chip and off-chip network traffic, latency issues, and bandwidth limitations in the literature. As a result of to solve those problems, the current research directions are shifted to the memory-centric computing approaches instead of compute-centric approaches to increase the performance further and provide energy-efficient approaches. We can classify the works to solve the memory wall into three categories, where the first one is off-memory processing, the second one is near memory processing, and the third one is processing in memory approaches. For the first approach, researchers are either trying to optimize the conventional memory technology or exploiting the new non-volatile memory technologies. For the near memory processing approaches, researchers are trying to offload some of the computations to the memory components, like near to the memory components, so that they can reduce the on-chip or off-chip memory traffic and reduce the traffic and latency. For the processing in memory approaches, they are trying to obtain the same thing by conducting computations inside those memory components, which can either be SRAM, DRAM, or non-volatile memory technologies. So the first work I'd like to share is the compute caches. In this work, they are trying to do the computation inside the caches, inside the SRAMs, but why not near to the cache? As you see, these are the in-place energy consumption of the in-place approaches, and the other columns are the energy consumption of the near-place approaches. As you see, there is a significant energy difference between in-place approaches and near-place approaches. So in-place approaches seem kind of promising in terms of energy efficiency, but there are some other constraints, limitations, which prevents us to implement them. In this work, they are trying to use the bit lines in the SRAM technology. Assume that your operands are listed in a row-wise, and you are kind of utilizing those bit lines so that you can to conduct the computations. To do so, they rearrange the existing cache elements so that they can cover some logical operations or XOR and NOT. And by utilizing those approaches, they can combine those logical operations to implement some basic functional operations such as copy, search, and compare. As I mentioned, the problem is operand locality, because we cannot be sure that the operands what we are looking for, what we want to computation on, are in the same bit line. They are not. We cannot be sure that they share the same bit line. But as you see, for example, as you see in the cache bank, for example, one of the operands can be in set 0 and the other one can be in set 12, for example. But their assumption or their baseline is that if the operands are page aligned, like if they are sharing the same page offset, you see that part, and they can share the same bit line. On top of this assumption, on top of this observation, they extended this cache, existing cache, and conduct some of those operations with the applications whose access behaviors are regular. And they observed the 1.9x performance speedup and 2.4 dynamic energy reduction. The second work is stream-based memory access specialization for the general purpose processors. The approach is to explore richer ISA semantics for memory access patterns, as what we did already for the vector instructions and loop accelerators. And their main contribution is to explore and efficiently deploy streams, which are simple memory access patterns, as mentioned, affine, indirect, and point-in shading in the paper. And they conduct an experiment where they tested the Cortex Suite benchmark and Spec CPU 2017 benchmark to see how much of the execution dominated by those streams. And as you see, more than half of the execution is dominated by the streams on average. So it seems promising. If we can accelerate the performance of those streams, we can obtain overall performance acceleration as well. Promising utilization approaches by using those streams are stream-based prefetching to hide the memory latency, semi-binding decoupled access to remove address computation, and optimize the memory interface such that we can maybe implement some stream-aware cache policies as well. But how to convey a higher level memory information and embed the stream information to the ISA, and how to take advantage of this information on the hardware. So they developed three different components for the ISA to operate the ISA extensions, which are stream configuration, stream step, and stream end. In the stream configuration, it keeps the streams unique behavior, streams width, like number of elements in corresponding to that stream, and stream stride. And in stream step, it is kind of just iteration, as what we use in for or other loops. And stream end specifies, acknowledges the core such that the stream is finished. These stream IC extensions can capture affine, indirect, pointer chasing, and coalesced access types inside the nested loops, even if there are some control overflows in those nested loops. This approach is extended, built on top of the LLVM compiler, and compilation process consists of 3 steps, which are recognizing streams and selecting the stream candidates, because some of those streams can be too complicated to accelerate or handle on the architecture, and code generation, in which the compiler defines the streams and maps the streams to the pseudo registers. That's the architecture implementation of these streams. This architecture is called stream specialized processor in the main paper. And as you see, there is an iteration map which tracks of the counts of the iteration of the induction variables for the stream step. There are stream either load or store FIFO to hold the coupled data. For example, if the core consumes the data, they can just access to this FIFO and consumes this data from this stream load FIFO. And the central component is the stream engine, which keeps the definition or the context of the stream and some parameters such as stream width and stream stride, and also keeps the stream states and induction variable. Induction variable is necessary to keep the current address of the current stream data. As a result of this approach, they obtained 1.37x speedup and 1.36 energy efficiency. The second work is Livia. In this work, they are trying to conduct the computation where data resides in the memory hierarchy for the irregular words. The motivation why they choose the irregular words as target is that, as you see, this is kind of irregular workload. I mean, to switch between 2 nodes, you need to jump from one node to one component to another. Let's examine it here. For example, that's the ideal mapping, but in the conventional systems, each request response, as you see, creates many traffic. For example, you check the red node, orange node, then the yellow node. For each of those requests and responses, it creates both latency to just read the blue node and creates some traffic throughout the memory hierarchy. Instead, there might be 2 approaches. One of them is processing in memory, and the other one is near memory computation. The problem in the processing in memory approaches, since we are conducting the processing in memory, as you see, all the computations firstly occurs in one of those memory banks, DRAM banks. Then we need to jump to the other memory banks, which is kind of hard. And this problem is the operand locality problem. Operand locality is hard for those irregular applications. But for the near memory approach, we can just map all data to the memory hierarchy as in the conventional system, like map all data into the cache hierarchy, and we can just jump across the nodes without going back to the core for each request. As you see, for example, it first reaches to the orange node, then it can directly jump to the yellow before going back to the core and requesting reaching the address for the yellow one and going to the yellow one. Instead, it can just jumps across the nodes, and it can just eventually it reaches the blue node, which is the target node, and go back to the core with the corresponding data. So Livia approach consists of 2 aspects. One of them is the memory services, and the other one is the memory service elements. Memory services are kind of some API to the user, where you can invoke the computations, which means that you can offload the computations to the near memory components streaming these memory service elements. For example, for the lookup example, if the key is what you are looking for, you can just directly return to the core. Otherwise, you can invoke the another computations by those MS invoke functions where you are in the memory hierarchy instead of going back to the core. So memory service elements are the architectural implementation of those memory services, like to run those functions. They implement memory service elements on the architecture. As you see, it resides in between L3 slice and L2 cache in the architecture. And there is a controller which controls the memory services and schedules these memory services to the execution engines. It is a configurable. In their work, they implemented those engines as FPGAs. In the execution engine, you can just compute what you are looking for as an address, as an either address or data to go. As a result of their work, the performance acceleration is from 1.3x to 2.4x for the regular workloads, and the dynamic energy reduction is from 1.2x to 4.7x. The third work is stream floating. This is kind of extension of the stream-based approaches because they are trying to target the same application behaviors. Also, as far as I remember, the authors are the same as well. So in this work, they are trying to change the mission of those caches such that those caches can act proactively and conduct the computations throughout the memory hierarchy, which is called decentralized computing. And they are trying to float those streams throughout the memory hierarchy. Aim is to decrease the request response traffic, lower the effective access latency, and reach less L3 bandwidth demand. But how does the system know this stream information? As I mentioned, the stream information can be embedded to the ISA with the stream-based work. But how does the system float those streams to the appropriate level of caches? For this purpose, they implement stream engines, which resides on core, L2 cache, and L3 cache slices. Stream core decides if a low stream should be floated. Stream engine on L2 creates the stream context, allocates the stream buffer, and it generates the stream address, and pack them and sends it to the L3 stream engine. Then L3 stream engine generates the destination address, as you see, for example, with this blue arrow, and send the data across the NOC. As a result of this work, the overall performance improvement for 4-way in order and 8-way 8-issue out of order architecture performance improvement is around 52% and 39% respectively, and energy efficiency is 64% and 49% respectively. Now Salah will go on. Thank you.
Thanks, Burak. I'll take it from here. Next, we'll talk about foldable logic reconfigurable computing paper that was published in 2020. Their approach was using the last level cache or part of it as a lookup table that is the building block for field programmable gate arrays or FPGAs. They aim for minimal changes to the system with low latency, cost, and power, and they were able to achieve 3 times the performance speedup with 6.1 performance per watt improvements. Next, we'll talk about the experiments that we have conducted. We were aiming to replicate some of the work that was presented in the literature review. So we ended up with the GemForge framework GitHub repository that was used in multiple papers. Here I'm listing only 2. It included multiple submodules, including LLVM, Gem5, and many others. One of the modules that it includes is DRAM Simulator 3. It's missing. It's forked from the original author, and they have modified it extensively for their research requirements in order to publish the papers. Sadly, however, we cannot get our hands on the modified version of the DRAM Simulator 3, so it wasn't able to compile in the beginning. Then when I tried to modify some files in order to make it to compile, I was able to do so. However, all the tests were failing because of the modified version of DRAM Simulator 3. Next, let's conclude. In this project, we have explored different approaches of near memory computation that explore the horizon of such approaches to computation. Even though we could not perform experiments, we have learned a lot about the topic from these experiments and papers. Lastly, I would like to thank you all for listening to our presentation. And finally, we'll have the references. Thank you.